Hey, welcome everybody. This is Mr. Gannon, and in this video, we're going to take a look at the 6.4 notes, which will focus on the rational root theorem. This will be something new that you guys haven't seen before, but it relates to how do we find zeros of polynomials that we might otherwise not be able to by factoring. So we have a theorem called the fundamental theorem of algebra that states any polynomial of degree n has at most n roots, both real and complex. Now, we've talked about that relationship before, where the number of solutions relates to the degree of the polynomial. So at this point, if we were to look at example 1, where it says how many x-intercepts does the following function have, we can look at the degree, which in this case is 5, but it doesn't tell us that there are 5 x-intercepts. What knowing the degree is 5 is tells us at most, so there are at most 5 x-intercepts. But in order to figure out how many x-intercepts it actually has, we would need some other information. And one approach might be to try to factor it, but there's no way that we've learned that's going to help us factor this. So another option would be to use like a graphing calculator and see what the graph looks like, because wherever the graph crosses the x-axis, those are the x-intercepts. So let's go ahead and pull up a graphing calculator. I'm going to go ahead and clear out what we have in there to begin with. All right, and the function that we're going to graph was 7x to the 5th power. I'm going to have to pull that back up, minus 4x squared plus 1. So get out of the exponent, minus 4x squared plus 1. And then if we hit graph, now I had my window adjusted. Let me go back and change it to a standard window. So we're going to zoom standard. And we can see the graph here. Now, what I'm not quite sure about is what's happening right at this little point down here. So I'm going to again adjust my window, just focusing on the y values. So I'm going to go from -1 to +1, hit graph. And what we'll see is the graph crosses the x-axis here at one point, but it didn't actually cross at this point. It got pretty close because, this is 0 and all the way up here is only 1. So it gets pretty close, but it doesn't actually reach the x-axis. So in this example, while there is at most 5 x-intercepts, there's actually only 1. All right. So by graphing, we can see that there is only 1. So we see the function has 1 x-intercept. So number 2 says, with a partner, try to solve or find the roots of the polynomial. Now, one thing we would look at is, roots are going to be the solutions, which can come from factors. So at first thought, we might want to try to factor this. And, when we look at it, there is no greatest common factor. So the fact that we have 4 terms, we might think, okay, maybe we can factor by grouping. So if we try to factor this by grouping, we group the first 2, we group the last 2. The first 2 have an x squared in common, and then we would have x plus 7 in our parentheses. Now the second 2, what they have in common is 3. So all we could factor out is 3. The other factor in parentheses would be 5x plus 3. So we have a problem here because this and this are different, which means this polynomial is not going to factor using any of the methods that we have learned how to. So unless we're going to go ahead and graph it like we did on the previous problem, we really get stuck in this situation. And that's where what we're going to learn today comes into play. So, without being able to, we're not going to rely on graphing. So what we're going to do in a situation like this is we're going to use what's called the rational root theorem or the rational zero theorem. And what the notes here say is if we know possible roots, all right, so if we know what the possible roots are, we can then use synthetic division to tell if they are actual roots. So how do we find possible roots? That becomes the question. Now, we have this rational root theorem that says that if f of x is a polynomial with integer coefficients, and if p over q is a 0 of f of x, then p has to be a factor of the constant, and q has to be a factor of the leading coefficient. All right, so that's how we're going to come up with our possible rational roots, or rational zeros. So in example 3 here, all it's asking us to do is make a list of possible rational zeros for f of x. In order to do that, what we have to do is identify p, which is the constant term. So this is p. And then q, which is the leading coefficient. All right, so we identify that p is 9. And what we're going to do is we're going to find all the factors of 9. The way I like to do it is I start small. So I know 1 is a factor, I know 3 is a factor, and I know 9 is a factor. All right. But in order to get 9, I could also multiply -1 by -9. So for each of these, we have plus or minus. And then for q, all right, q was 2 in this situation. Well, the factors of 2 are simply 1 and 2. Again, they could be plus or minus. The rational root theorem tells us that the possible rational roots are going to be combinations of p over q. So we're going to make our list of possible zeros. And I'm going to do 1 divided by 1, which is 1. 1 divided by 2, which is 1/2. Then I'm going to do 3 divided by 1, which is 3. 3 divided by 2, which is 3/2. 9 divided by 1, which is 9. And 9 divided by 2, which is 9/2. So those are, and again, plus or minus, those are the possible rational zeros. Now, there's going to be more work involved to decide which ones are actual zeros, which we'll get into here in a little bit. But one of the things we need to be able to do in this lesson is just be able to identify what are the possible zeros. So just a quick recap. P is your constant. Q is your leading coefficient. All right. So what we have highlighted here, these are the factors of P, and then these are the factors of Q. And the possible rational roots are going to be anything that we can get from doing P over Q. All right, we're going to do one more example. I would recommend that you pause the video and try this on your own first. So in this example, we want to make a list of all possible roots of this function. So here's our constant, there's P. Here's our lead coefficient, all right, which in this case is going to be 1, even though it's not written. So for factors of 12, I know it's 1, 2, 3, 4, 6, and 12. And again, each one of those can have the plus or minus in front. And then Q is going to be 1. So the only factors of 1 are going to be plus or minus 1. So then at that point, we can go ahead and make our list of possible rational zeros, which is P over Q. So in this case, each one of these factors of P is going to be divided by plus or minus 1. So 1 divided by 1 is 1. 2 divided by 1 is 2. 3 divided by 1 is 3. 4 divided by 1 is 4. 6 divided by 1 is 6. And then 12 divided by 1 is 12. Each of those gets the plus or minus. Those are the possible rational roots. So the key is understanding what's P, what's Q, and what are the factors. All right, now we're going to take this to the next level. All right, now we're going to use synthetic division to see which of the possible roots are actual solutions. And there's a little reminder here. It says if it is a solution, the remainder needs to be equal to 0, because that means that it divides evenly into it. Now, in this example, if we want to figure out which one is possible, it really becomes a guess and check idea at this point. So we might want to start with some simple numbers like 1. Well, if I do synthetic division with 1, then in this case, I'm going to have my coefficients of 1, 1, -8, -12. And this would be where doing synthetic division over long division is going to save a lot of time. Bring down the 1. 1 times 1 is 1. Add, you get 2. 1 times 2 is 2. If we add here, we get -6. 1 times -6 is -6. That's -18. That's not 0, so 1 doesn't work. Now, we could repeat this process, all right? And we could just keep trying different numbers. To speed this up, just because for the sake of the video, I'm not going to go through every single possibility until I find one that works. So if I were to graph this function, just to kind of speed this up, if we have x to the 3rd power, and then it was plus x squared, so plus x squared minus 8x minus 12, so minus 8x minus 12, and we graph. Okay. What I can tell is I can see that our graph is going to cross the x-axis here at -2, but also here at 3. So I know that those have to be solutions, okay, which are going to be roots. So I'm going to pick one of those. In this case, I'm going to go ahead and pick 3. So if I chose 3, which is part of our list, and I do synthetic division, I've got 1, 1, -8, -12. I'm going to bring down the 1. 3 times 1 is 3. 1 plus 3 is 4. 3 times 4 is 12. -8 plus 12 is 4. And 3 times 4 is 12. -12 plus 12 is 0. So there is that remainder of 0. Remember, when you do synthetic division, this is your remainder, this is the constant, this is x, and this is x squared. So we now know a couple things. We know that 3 is in fact a solution. All right, so if I'm trying to find what are the actual roots, I know that the roots are going to be x equals 3. But I also know that when I divided by, basically x minus 3 as the factor, I get this polynomial x squared plus 4x plus 4, which I can set equal to 0 and solve to find the other roots. And when I solve this, I can factor. So I'm going to do 2 binomials, x and x. Positive here means they're the same, so they're both plus. And then I need factors of 4 that are going to multiply by x and x and add to 4x. It's going to be 2 and 2. And what I find out is that the other solutions are -2 and -2. So the roots of this polynomial end up being x equals 3 and -2. All right. Now, I will say we did cheat a little bit because I used the graph to kind of help find one of those that's going to work. If you don't have access to a graphing calculator, then what you would have to do is you would just have to keep trying different values here using synthetic division until you come up with the remainder of 0. Once you get that remainder of 0 and the resulting polynomial is x squared, you should be able to then solve by either factoring or possibly using the quadratic formula. All right, so we've got a couple more examples. Let's see, example 5 here says, which of the following are not, that's key, not possible solutions, okay? And again, it's not saying which ones are not solutions, it's specifically saying which ones are not possible solutions. So we can get our list of possible solutions by finding factors of p and q. So in this case, the factors of p are going to be plus or minus 1 and 3. And then the factors of q are going to be plus or minus 1 and 2. So the way that we can determine if it is a possible is if I can take one of my blue factors and divide it by my green factor to get it. So 2 I can't use 1 or 3 on top to get 2. So 2 is not a possible root. Then I would check -3 over 2. Well, -3, 2, that does work. So I eliminate that. It's not an answer. 1 is going to come from 1 divided by 1, so that is going to be a root. 1/2 is coming from 1 over 2, so that is going to work. -2 over 3, well, I cannot take factors of p divided by q and get 2 over 3, so that's going to is not a possible solution. All right, 3 comes from 3 divided by 1, so that is a solution or a possible solution. And then 1 over 3 I cannot get, so that is not going to be a possible solution. So you got to make sure you read these carefully. This time it was which ones are not possible, and those are the ones that have the boxes. So 2, -2/3, and 1/3 are not possible solutions. All right. Other types of problems we're going to run into. Number 6. It says the equation x cubed minus 4x squared plus 4x minus 16 equals 0 is graphed at the right. It says use the graph to help solve the equation and find all the roots. So that's going to be important. Now, taking what we've learned in the past and kind of what we've talked about today, we can look at this graph and we can see that this graph is crossing the x-axis at 1, 2, 3, 4, at +4. The x-intercepts are solutions. So what that's going to allow us to do is take and do synthetic division using our root of 4. I'm going to list the coefficients of 1, -4, 4, and -16. All right, we're going to do the synthetic division by bringing down the 1. 4 times 1 is 4. Add to get 0. 4 times 0 is 0. We add those to get 4. And then 4 times 4 is 16. We add and we get 0. So that remainder of 0 just confirms that 4 is a solution. All right. And now what I'm left with, remainder, constant, x squared. All right. So one of our solutions is x equals 4. You might want to write it over here so you don't forget about it. But then I have this function, x squared plus 4 equals 0. Now, there's a couple different ways you could solve this. The easiest way is going to be to isolate the x squared and solve it by square rooting. So if we subtract 4, x squared is going to equal -4. Then we can square root both sides. Square root of x squared is x. And then over here, the square root of -4 is going to be 2i. And then one thing you want to remember is whenever we solve by square rooting, we got to include the plus or minus. So the other solutions are, there's 2 more of them, +2i and -2i. So we got plus or minus 2i. And the reason that you don't see those on the graph is because they're imaginary. So imaginary solutions will not show up in the graph. All right. Looking at 7. Now, 7 wants you to find all possible roots of the function. We do run into a slight problem because there's no constant. But what you can do in this problem is when you set it equal to 0, you can factor out the x. So we take out the x. Now we're going to have 2x cubed minus 3x squared plus 7x plus 12. And then in that case, p is now 12 and q is 2. So we would identify the factors of 12, which are going to be plus or minus 1, 2, 3, 4, 6, and 12. And then we take factors of q, which are plus or minus 1 and 2. All right. Now, the possible rational roots, we're going to do p over q. And in this case, p over q becomes plus or minus. All right, so I'm going to start with 1, and I'm going to divide it by each of these. So 1 divided by 1 is 1. 1 divided by 2, 1/2. 2 divided by 1 is 2. 2 divided by 2 is 1. Now, I've already got 1 I'm not going to repeat it. 3 divided by 1 is 3. 3 divided by 2 is 3 halves. Then I go to 4. 4 divided by 1 is 4. 4 divided by 2 is 2, which I already have, so I don't rewrite it. 6 divided by 1 is 6. 6 divided by 2 is 3. Already have it. And then 12 divided by 1 is 12. 12 divided by 2 is 6. Already have it. Now, the reason that you don't want to keep repeat numbers that you already have is right now there's 1, 2, 3, 4, 5, 6, 7, 8. But I have to multiply that by 2 because of the plus or minus. So there's 16 possible roots in this situation. Now, I could go through the whole process of doing synthetic division. But again, for the sake of the video, I'm going to go ahead and use the graphing calculator to graph this and just get an idea of where it's crossing the x-axis. So we've got 2x to the third power minus 3x squared and then what was it? Plus 7x plus 12. Hit graph. All right, and now I can see that, well, let me go ahead and zoom out here real quick just so you guys can kind of see. So standard. So our graph, we can only see part of it, and it only appears to cross at -1. So that's what all that tells me to do is I'm going to do synthetic division with -1, and I'm going to use what's in the parentheses here. All right, so it's 2, -3, 7, and 12. Bring this down. -1 times 2 is -2. If we add, we get -5. -1 times -5 is 5. If we add, we get 12. And -1 times 12 is -12. If we add, we get 0. So again, that confirms that -1 is in fact a solution. So right now, our solutions are going to be x equals -1. From up here, which you might miss if you're not careful, would be 0 would be a solution. So we want to include that. So -1 and 0. All right. And then from the division, I've got remainder, constant, x squared. So this would be 2x squared minus 5x plus 12. We want to set this equal to 0. Now, if you were to try and factor this right now, it's not going to factor. Okay? You could try it. You could try all the combinations. It won't work. So at this point, the only alternative we have to solve this equation is the quadratic formula. So we learned the quadratic formula back in chapter 5. In order to use it, we're going to identify A. So A in this case is 2, B is -5, and C is 12. We're going to plug it in. X equals -b plus or minus the square root of b squared minus 4 times A times C all over 2 times A. Now, just kind of a reminder, in case you forgot the formula, I'll write it up here. So it's x equals -b plus or minus square root of b squared minus 4ac all over 2a. At this point, we need to simplify this down. So -5 becomes +5 plus or minus. Square root of -5 is +25. A negative times a positive is going to be a negative. 4 times 2 is 8. 8 times 12, that's 96 over 4. All right, if we keep simplifying, we've got 25 minus 96. So what is that? -71 over 4. And then the only thing we can do to simplify this down anymore is take out the I. So what we would include to our solutions are 5 plus or minus I root 71 over 4. Now, in this case, it says find all possible roots. This right here would be our list of all possible roots. All right. We had a degree of 4 at the beginning of the problem. We should expect there to be 4 answers. And that's what we get when we take our rational roots and our imaginary roots. All right, guys, hope you found the video helpful. If you have additional questions, go see your teacher or maybe go back and try to watch the example again. Have a good night.